Good afternoon, students. Let us continue to see there are a few important topics from coordination chemistry. The screen share ஆக மாட்டேங்குதுங்க. இப்போதான் ஆச்சு. Okay. Thank you. Okay, now let us look at crystal field stabilization energy. In this, we are going to learn pairing and also Hund's rule. We all know that previous classes we have learned that when the crystal field theory, when under the influence of ligands, the d orbitals undergo splitting, we saw. Okay, so it has consequences. For example, the stability, reactivity, and magnetic properties, all of them are affected by this splitting of d orbitals. Okay. Suppose if we consider hexa aqua complex. Okay, first let us consider hexa aqua complex M H2O 6 times 3 plus. It's a cationic complex where M is titanium, vanadium, and chromium. And because the complexes are octahedral, they all have the same energy level diagram. That is titanium hexaqua complex and vanadium hexaqua complex and chromium hexaqua complex. All of them will have the same energy level diagram. That is, we have T2G and EG level in T2G, we have three orbitals will be there. The dxy, dyz, and then dzx or xz. And then we have EG. In the EG orbitals, we have in the EG orbital, we have z squared and dx squared minus y squared. Okay. And then the middle line, actually, the dotted line is the barycenter, where that represents the before splitting, the energy level before splitting. When under the influences of the ligands, the energy level of the d orbitals raised to the barycenter. From there, after that, it splits. Okay, so lower level and the higher level it splits. T2G levels or energy less orbitals, EG orbitals or energy high orbitals, they split. And the splitting energy we saw for the T2G electrons. So each electron contributes 2/5 minus, actually, since the energy lowest, it is minus, so minus 2/5 delta O. And then for each electron in EG level will be plus 3/5 delta O. Okay, that is octahedral crystal splitting. And titanium 3 plus, last class we have seen titanium 3 plus. Titanium 3 plus, titanium atomic number is 22. Okay, there are 4 electrons in the valence orbital, 4s2 and 3d2 and 3. We are going to remove 3 electrons from titanium, so we get D1 configuration. Okay, so D1 and only 1 electron in the T2G level. And then if you consider vanadium 3 plus, so vanadium 3 plus is atomic number is 23. So we are going to remove 3 electrons. So 23 means 2 plus 3, 5 electrons, and that out of 5 we are going to remove 3. So you get D2 configuration. Okay, so 2 of the T2G levels will be filled with 1 electron each. And then next, chromium 3 plus. So chromium is 24, atomic number 24, and the configuration is 4s1 3d5. Okay, so 4s1 3d5, 6 electrons. We are going to remove 3 electrons, so the configuration is D3. So 3d3 configuration for chromium plus. And so each of the 3 electrons occupy 1 orbital of T2G level. Okay, this is the splitting of titanium, vanadium, chromium. Whether it is high spin, low spin, only 3 electrons are there. There is no change. Whether the ligand is a high spin ligand or low spin ligand, they are going to be same, because they all of them, titanium 3 plus, vanadium, chromium 3 plus, they are going to form a complex, inner complex, because they are going to use the 3d orbitals and D2sp D2sp3 configuration, D2sp3 configuration, and they are going to be high spin, whether it is strong ligand or weak ligand. Okay, and if you look at titanium 3 plus and then vanadium and chromium 3 plus, chromium 3 plus, they have all high spin complexes, and if you go chromium 2 plus, okay, chromium 2 plus can have high spin or low spin, depends on the ligand, because as soon as you have the D4 configuration, the D4th electron can can pair up with the T2G level, or it can go to the EG level, depends on the energy splitting, and that depends on the ligand. Okay, if you look at titanium, we have 1 unpaired electron, and then vanadium 3 plus, we have 2 unpaired electrons, and then chromium we have 3 unpaired electrons. Okay, they are going to be parallel according to Hund's rule. Now, for each of these complexes, we can calculate a crystal field stabilization energy which is the energy difference between the complex in its ground state and in its basically that excited state, that splitting state. So the equation is crystal field stabilization energy is equal to minus 2 by 5. That is T2G level. The electrons into multiplied by X, the X is number of electrons in T2G level. So if the each electron contributes minus 2 by 5 delta O to the crystal field stabilization energy, and then plus 3 by 5 Y if there are electrons in the EG level, that is going to be plus because the energy is increased. So 3 by 5 Y times Y is number of electrons in EG level. The whole thing is multiplied by delta O and plus ZP. And ZP, so ZP is then Z is number of unpaired electrons present in the electronic configuration. Okay, so same thing we can write it as so first one fraction, and we are writing it as a decimal number. So sometimes the question they'll give, just simply give a fraction they may give, or sometimes they'll give the decimal value. Okay, so I would recommend we always calculate as a fraction and then convert that fraction into decimal. Sometimes you can directly use the decimal, that is 2 by 5 is 0.4. So minus 0.4x plus 3 by 5 is 0.6. So plus 0.6 times y multiplied by delta O plus ZP. Okay. And then P, as I said before, is the pairing energy. The pairing energy is again going to be positive because when you already there is an electron in the orbital, and you are going to put another electron into that, and there is going to be repulsion between the electrons, and for that causes increase in energy. So it is plus. Okay, so minus 2 by 5x because this, since why it is negative, because the energy level decreased. The T2G orbitals that that they are actually in the octahedral field, the ligands are approaching the metal atom along the axis. Okay, so whichever orbital along the axis, they are going to experience more repulsion. And then the orbitals which are present in between the axis, for example dxy, they are present in between the axis. Lobes are present in between the axis. What is the meaning? It means the electron density of electrons present in dxy is in between the axis. It is not present in the it is not present along the axis. So the repulsion will be higher along the axis. So dx squared y squared orbital and dz squared orbital going to be the increased energy, and the other three decreased energy. Okay, so we have to put minus. Now that this also we know, if the delta O, that is if the gap between the T2G level and EG level is higher. Okay, when it will be higher, the high spin, strong ligands. When a strong ligand approaches, it's going to increase the splitting gap. That delta O is going to be high. So if the delta O is going to be high, we are going to get low spin. Low spin means the electrons are going to be paired because the pairing energy is less compared to the gap. Okay, so if you want to put the electrons in the higher energy level, the electron would prefer to go for pairing because that is less. Whichever is the less energy path, whichever uses less energy, that only the complex prefers. So if it is a low spin, it means delta O is higher than P. If delta O is higher than P, you are going to get low spin. It means electrons are going to be paired. If it is high spin, that is if the delta O splitting energy is less compared to the pairing. If the splitting energy is less, the electrons would prefer to first to occupy individually, and then pairing will take place. Okay. So because the delta O depends on both the metals and the ligands, of course, it determines the spin state of the complex. Okay, now there are rules of thumb. Now you can memorize this and then think that 3D complexes are high spin with weak ligands. Okay, complexes formed by 3D series. That is the first transition series. That is scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. Okay, these 10 belongs to 3D series, and these complexes, if the ligand is a weak ligand, they are going to form high spin complexes, and strong if the ligands are strong, they are going to form low spin complex. Okay, and then another thing is high valent 3D complexes. Okay, high valent, that also you can remember. High valent 3D complexes, that is, suppose if a metal complex which can have two oxidation state, less and have more, whereas that is cobalt 3 plus, cobalt 2 plus, iron 2 plus, iron 3 plus. So generally, if the high valent complexes tend to form low spin. Okay, and then 4D and 5D series. Okay, 4D and 5D series, we have 4D series, the second transition elements, where we have the metals. Metals, if you look at below, iron, cobalt, nickel, copper, zinc, we have ruthenium, rhenium, palladium, silver, cadmium. Those metals belong to 4D series. And 5D series, we have osmium, iridium, platinum, gold, mercury, all of them comes under 5D series. These metals, generally they form low spin complexes. Okay. And then generally note the high and low spin states occur only for 3D metal complexes with electrons between 4 and D, with electron D 4 and 7. Now pay attention. If the D number of electrons in the D is between 4 and 7, then only you have to worry about high spin and low spin, because below 4, that is 1, with D orbitals 1, 2, 3, they are going to form always high spin complex. Okay, so 1, 2, 3, D orbital, D electron configuration, if it is 1, 2, 3, it is going to form only high spin complex, because we have 2G orbitals are there. So these 3 electrons going to occupy one each. So only high spin. So when we have to worry about high spin and low spin, if the D electron configuration is between D4 to D7, and if the D electron is 8, 9, 10, if the D electrons are 8, 9, 10, then they are going to have mostly T2G orbitals are completely filled, and then T2G levels, how many we need? 6 only we need, but the electronic configuration is 8, 9, 10. So 6 will go to the T2G level completely filled, all of them paired, and then you have 8 means a D configuration. 8 means 2 electrons left, that will go to EG. If it is 9 means 3, it will go to EG. If it is 10 means completely filled. So D configuration, D electron configuration, if it is 1, 2, 3, they are going to form high spin. Okay, no matter what type of ligand. If the D electron configuration is D4 to D7, okay, 4, 5, 6, 7, only these 6 D configurations only, high spin and low spin complexes are possible. And then if the D configuration is 8, 9, 10, then they are going to have all the T2G level will be completely filled, and then we have other electrons will go to the EG level. Okay. Now let us find out the crystal field stabilization energy for a couple of examples. Okay. Now first one, cobalt hexa aqua, cobalt 2. Okay, hexa aqua cobalt 2. It should be the bracket should come to the front. So hexa aqua cobalt 2. Okay, cobalt 2. Here it is given. The example is cobalt 2. And then cobalt 2, it contains D7. Okay, Hauser cobalt atomic number 27. So 2 electrons, 12, 7, 2 plus 7, 2 from 4s2, 7 from d orbital. So we are going to remove the d orbital, 2 electrons from 4s. So you get d7 configuration. Okay, so H2O is a weak complex. H2O is a weak complex. Remember that spectrochemical series, you remember the ligands which have halide ions, are weak. Oxygen, if it is an donor atom, generally they are weak. And then sulfur, if the donor atom is sulfur, they are weak. And what are the strong ligands? Ligands with the donor atoms, nitrogen, such as nitrogen and um, carbon, phosphorus. These are all strong ligands. Okay, so H2O is actually oxygen is the donating donor atom. It is oxygen, so it's going to be a weak ligand. So weak ligand means that delta O will be small. So weak ligand, we saw delta O is small, and so it's going to form high spin complex. Um, let us look at no, so actually this is give me a second, students. Give me a second. There is some, yes, because it's to a D7 configuration means you need to have only one unpaired electron in the EG level, the 6. Okay, 6. Since it is a weak ligand, we're going to, oh, no, correct only. Now look at the configuration, electronic configuration D7. Okay, D7, it is a weak ligand. So what we are going, there are 7 electrons are there. We have to distribute the electrons into the orbit. So what we are going to do, there are 5 orbitals are there, T2G and 3 T2G and 2 EG orbitals are there. First, we are going to fill all the electrons with 1, 1. So 5 electrons we are going to fill, and remaining 2 electrons we are going to pair it with the first 2 T2G orbital. Okay, so this is the configuration given. So you will have 2 electrons in the first T2G level and 2 electrons in the second T2G orbital, and then only 1 electron in the third T2G orbital, and then we have both the EG orbitals will have 1 electron each. So if you count the number of unpaired electrons here, number of unpaired electrons 3. Okay, it's going to form a high spin complex. And let us find out the crystal field stabilization energy. The formula is minus 2 by 5 x plus 3 by 5 y into delta O plus z into p. What is number of electrons present in the T2G level? We have 5 electrons are there. Okay, 2 paired electrons or 2 paired orbitals and 1 unpaired orbitals. 5 T2G orbital electrons are there, and 2 EG electrons are there. Okay, so x is equal to 5, y is equal to 2, and then z number of paired electron orbitals which contain paired electrons is 2. Okay, so 2 orbitals are paired. So the equation will become minus 2 by 5 into 5, because the number of electrons present in T2G is 5, plus 3 by 5 into 2, number of electrons present in EG level 2, and then the whole thing multiplied by delta O plus 2 times P, because Z is equal to 2. Now, I'm going to first ask, I would recommend you always try to make the fraction, and then if it is necessary, you can convert it into decimal. So I'm going to first convert this one into fraction. So 5 2s are 10 minus 10 by 5 plus 2 3s are 6, 6 by 5. Whole thing multiplied by delta O plus 2p. So minus 10 plus 6, we have minus 4 by 5. Delta O plus 2p. So minus, sometimes the options will be minus 4 by, in the fractions will be there. Sometimes it may be in decimal point. So if you convert this one to decimal, 4 by 5 is 0.8. So minus 0.8 delta O plus 2 times p, 2p. Okay, this is about weak Ligon. Let us look at the cobalt, the same cobalt 2 plus hexacyano cobaltate 2 ion. Okay, hexacyano cobaltate 2 ion. Again here, this give me a second. This square bracket should come to the front. So hexacyanoferrate, hexacyanocobaltate 2 is also an octahedral D7 complex, but here it's a strong ligand. Cn minus is a cyanide ion, is a strong ligand. So what we are going to do is that's pairing low spin complex. It's going to form. So what happens in strong field ligand? First, first we are going to put all the electrons. First, we have to fill the T2G level. So we have 3 orbitals are there. So we are going to put 6 electrons. First 1 1 1 and then pair all the 3 orbitals, then you get extra 1, it goes to the EG orbital. Okay, so now calculate how many electrons present in T2G level. We have 6, and then there is 1 electron present in EG level. So what you get is now 6 electrons in T2G, 1 from EG, and then number of paired electrons 3. Okay, so if you substitute in the formula, you get minus 2 by 5 into 6 plus 3 by 5 into 1 multiplied by delta O plus 3p. 3 orbitals, 3 orbitals, all the 3 T2G orbitals are paired, so 3p, and then 3 times pairing energy. So 6 2s are 12 minus 12 by 5 plus 3 by 5. So you get minus 9 by 5 delta O plus 3p. So minus 9 by 5 is minus 1.8 delta O plus 3p. Okay, so this is how you calculate the crystal field energy. Now, as I told before, the 3D complexes can be low spin or high spin depending on the ligand. Okay, if it is up to, generally up to D3, always high spin, and D8, we are going to have generally all the T2G will be filled. Okay, all the T2G will be filled, 6, and then 7 we are going to have 1, and then if it is 8, we are going to 2G. Both the EG level will be 1 1, and then 9 10 will be all of them will be paired. And then 4 and D, 5D, 4D and 5D complexes always low spin because delta O is large. And then maximum crystal field stabilization energy for 3D and D8 cases. Okay. For with the weak ligands, if the field ligands are weak and the D configuration is D3 and D8, then you will get maximum crystal field stabilization energy. And for D3 to D6 with strong fields ligands, D3 to D6, again you will get maximum crystal field stabilization energy. Okay, now look at the color and spectra of transition metal complexes. Now vanadium in the 2 plus hexa aqua complex can have 2 colors, one lilac and green. And similarly, there is a vanadium oxide complex, another complex, it can also form blue and yellow. Okay, same vanadium 2 plus state can exist in 2 different colors. Why is this? This is again because in vanadium we have three odd electrons are there, single electrons or the unpaired electrons are there. And then these three electrons, when it is excited, they can go from the ground state to, there are two orbitals in the EG level. Okay, either they can go to z squared or x squared minus y squared. And there is a small difference between dz squared and x squared minus y squared. That is the reason. So if it goes to dz squared, then it will give one color, and if it goes to x squared minus y squared, it will give another color. That is the reason you get different colors. Okay, and already we saw that coordination complexes are highly colorful because of the DD transitions. Okay, DD transitions of the metal complexes explained by crystal field theory. Now let us look at one of the question from NEET. They have asked this question: low spin complex of D6 cation in an octahedral field have following energy. Okay, low spin complex of D6 cation. Okay, D6 cation and then low spin complex. அப்படி இருக்கும்போது what is the octahedral field following and what is the crystal field stabilization energy or octahedral field energy அப்படின்னு கொடுத்து they have given an all option கொடுத்திருக்காங்க, and then you have to find out. Okay, so D6 cation, low spin D6 cation. Okay, low spin D6 cation நம்ம என்ன பண்ண போறோம் அப்படின்னா low spin அப்படின்னு சொல்லியாச்சு. low spin அப்படின்னா என்ன பேர் பண்ணணும்னு அர்த்தம். 6 வந்து பேர் பண்ணணும். ஓகே, so 6 electrons are there, 6ஐயும் பேர் பண்ணோம் அப்படின்னா என்ன ஆகும் அப்படின்னா all the T2G level will be paired. Okay, there is no electrons will be there in the EG level. Okay, so now what happens, you can use, I told you both the equations you can use. இதுல வந்து நம்ம பார்த்தோம் அப்படின்னா let us use this one. I just want, give me a second. I want to use this formula. Let us substitute here. Okay, in D6, we have all the x is actually 6, and then there are no electrons, 0 in the EG level, and the number of pairing electrons, number of orbitals with paired electrons 3. So it becomes 0 into 3 by 5 is 0. So we have just minus 12 by 5 and cancel the whole thing. Minus 12 by 5. Okay, minus 12 by 5. Okay, that's what they had given. They have given the option as, see, look at the option, minus 12 by 5 delta P, delta O plus so one of the options, minus 12 by 5 delta O plus P, minus 12 by 5 delta O plus 3P, minus 2 by 5 delta O plus 2P, minus 2 by 5 delta O plus P. So what is the correct option? Minus 12 by 5 delta O plus 3P. Option B is the correct answer. Okay, because D6 configuration, low spin D6 configuration means all the electrons should be paired. Okay. Now, which of these statements about hexacyanocobaltate 3 is true? Okay, so what they have given, the first statement, hexacyano COCN6 3 minus has 4 unpaired electrons and will be in a high spin configuration. And then COCN6 3 plus 3 minus has no unpaired electrons and will be in a high spin configuration. No unpaired electrons and will be in a high spin configuration. And then COCN6 3 minus has no unpaired electrons and will be in a low spin configuration. And then COCN6 3 minus has 4 unpaired electrons and will be a low spin configuration. So quite confusing. So best thing is just find out the configuration of cobalt. Okay, cobalt, here's hexacyano of cobalt 3. Okay, why? Cn minus, first another thing, Cn minus is a strong ligand. It is going to form if it is a strong ligand, it's going to form a low spin complex. Okay, it cannot form a high spin complex. Strong ligands will always lead to low spin complex. Okay, so we can high spin, we can remove, that is A and B option, we can remove. So low spin, low, and then C and D. Okay, and then what is the cobalt electronic configuration? Cobalt atom is 27, so it is 4s2 3d7, and we are going to remove 3 electrons, so it's going to be 3d6. Okay, 9 minus 3, so 27. Just I told you, see, 27, 2 plus 7, 9 electrons are there, and we are going to remove 3, so you are going to get d6. Okay, cobalt 3 plus is d6. D6 in high spin complex, low spin, these high strong ligands, it's going to form only low spin complex, and it has all the 6 electrons are going to be paired. There is no unpaired electrons and will be a low spin configuration. That is option C is the correct one. Okay, so you must know the strong ligands and weak ligands. What are the strong ligands? What are the weak ligands? And then you should also know this atomic number of the elements. Mostly they might give in some problems, they'll give some, they may not give. So you be prepared for that. Or you have to go back and forth and see where it is given. That's waste of time. So better always try to easy numbers. It's not so complicated. If you remember the order, scandium, titanium, vanadium, chromium, manganese. Okay, so 21, 22, 23, 24, 25. Manganese 25, chromium 24, and then iron, cobalt, nickel 26, 27, 28, and then copper 29, zinc 30. So it is easy. And then next, give me a second. Now, another question, 2017, they have asked, pick out the correct statement with respect to CN6, manganese, Mn, CN6, 3 minus. Okay, Mn, CN6, 3 minus. So it is now immediately Mn6, CN6, 3 minus. What is the oxidation state of Mn? Cyanide வந்து minus 6 minus வெளியில 3 minus இருக்கு. So -3 in this -6 அந்த பக்கம் கொண்டு போனா it will be +6, so it will be +3. So manganese is in +3 state, manganese in +3 state. So what is the atomic number or electronic configuration of Mn3 plus? So generally Mn3 plus Mn atomic number is 25. Atomic number of manganese is 25. The 7 electrons are there. 2 plus 5, 7 electrons are there, and then 2 electrons are there, and then 2 plus 5, 7 electrons are there, and we are going to remove 3, so you have 4 electrons are there, and cyanide is a strong ligand. Okay, 4 electrons are there, and then so how will you place the 4 electron? We are going to put all the 4 in according to valence bond theory. So sp3d means valence bond theory. Okay, whenever T2GeG crystal field, all those comes in crystal field theory, but whenever we talk about this hybridization, it goes to valence bond theory. So valence bond theory, we are going to arrange the d orbitals and then place the electrons. So 4 electrons. What is the electronic configuration of Mn3 plus? Mn3 plus is D4 configuration, and the cyanide ion is a strong ligand. So what happens? We're going to place the ligands. 4 ligands are there, so all the d orbitals will have 1 1 1, and then except one will be empty. And since it is a strong field, pairing will be there. We need 2 d orbitals, so one is already empty, so one of them is going to be go to the pairing. Okay, out of 4, 1 will be paired. So when we have 2 unpaired electrons will be there, and remaining d orbital, it's going to use the d2sp3 hybridized orbital and octahedral. Okay, so oxidation state of Mn, it is +3. Electronic configuration of Mn 27, 4s2 3d5, and then Mn3 plus is 3d4. And see, cyanide is a strong field, thus it causes pairing of electrons in 3d orbital. So it's going to have octahedral geometry and d2sp3. It's the inner spin complex. Many things, inner spin complex, it has a paramagnetic effect because 2 unpaired electrons are there, so paramagnetic. Another question they have asked is correct increasing order for the wavelengths of absorption in the visible region for the complexes of CO3 plus E's. Okay, correct increasing order for the wavelength of absorption in the visible region for the complexes. Already we know that the complexes are highly colored, full, and they are in the visible region. So they have given all of them cobalt 3 plus complexes கொடுத்திருக்காங்க. So increasing order for the wavelength of absorption. Okay, so before we look into this, let us see. நம்ம வந்து weak field, long field வந்து approximately we know. Okay, I told you என்ன பார்த்தோம், ஹாலஜன்ஸ், டோனர் ஆட்டம்ஸ் வந்து ஹாலைட்ஸா இருந்தா, ஆக்சிஜனா இருந்தா, இல்ல சல்ஃபரா இருந்தா, they are all generally weak ligands. If the donor atoms வந்து கார்பனா இருந்தா, நைட்ரஜனா இருந்தா, generally they will be strong ligands அப்படின்னு பார்த்தோம். ஓகே, ஸோ அமோனியா, இங்க என்னென்ன லிகான்ஸ் கொடுத்துருக்காங்க, அமோனியா கொடுத்துருக்காங்க, டயத்தில் அமீன் கொடுத்துருக்காங்க. ஸோ அமோனியாவும் டயத்தில் அமீனும் இருந்ததுன்னா அந்த சீரியஸ்ல ஞாபகம் வச்சுக்கணும், அமோனியா will come less. Okay, diethylamine வந்து will have more. And so we have let us இதுல வந்து பாத்தீங்க அப்படின்னா there is H2O is a weak ligand followed by ammonia followed by diethylamine. Okay, இது அந்த ஆர்டர்ல தான் போகுது. Okay, now remember this one. The splitting energy ஞாபகம் வச்சுக்கோங்க. The splitting energy, if it is a strong field na the energy ஜாஸ்தி ஆகுதுன்னு அர்த்தம். Okay, the energy will be higher for stronger ligands. Okay, the strong strength increase ஆக and the energy increase ஆகுதுன்னு அர்த்தம். Okay, so if it is a weak ligand, the energy will be less. Okay, so according to the energy arrange பண்ணுங்க, எதுக்கு வந்து கம்மியா இருக்கும், வாட்டருக்கு கம்மி, இட்ஸ் அ வீக் லிகாண்ட், வாட்டருக்கு கம்மியா இருக்கும், அடுத்தது வந்து அமோனியாக்கு கம்மியா இருக்கும், தென் ஃபாலோட் பை EN3. ஓகே, ஜாஸ்தியா இருக்கும். ஃபர்ஸ்ட் கம்மி வாட்டர், அதுக்கு அடுத்தது வந்து ஜாஸ்தியா இருக்கிறது அமோனியா, அதுக்கப்புறம் ஹையஸ்ட் வந்து கிவன் 3ல வந்து ஹையஸ்ட் வந்து EN3ல இருக்கும். ஓகே, என்னது எனர்ஜி, ஏன் அப்படின்னா லிகான்ஸ். ஆனா இங்க என்ன கேட்கறாங்க, எனர்ஜி கேட்கல, வேவ் லென்த் ஆஃப் அப்சார்ப்ஷன் கேட்டிருக்காங்க. அப்ப எனர்ஜி இன்க்ரீஸ் ஆச்சுன்னா வேவ் லென்த் வந்து டிக்ரீஸ் ஆகும். Okay, if energy is increased, wavelength will be decreased. அப்ப அந்த ஆர்டர் வந்து ரிவர்ஸ்ல போடணும். எனர்ஜி பாத்தீங்கன்னா H2O, NH3, En வந்து ஜாஸ்தியா இருக்கு. And then so if it is wavelength means the reverse order. So first has to be CO, En3 should be there. Ethylene diamine ligand first வரணும், followed by NH3, followed by H2O. That is option D. Okay, so increasing order of crystal field energy பாத்தீங்கன்னா it is H2O, NH3, En. Whereas E equal to Hc by lambda, அந்த ஃபார்முலா நமக்கு தெரியும், E equal to Hc by lambda. So if energy increases, lambda decreases. If energy decreases, lambda increases. Okay, for that you run. So first arrange the ligands in the energy wise, and then accordingly we can select it. So increasing order of wavelength of absorption பாத்தீங்க அப்படின்னா it will be so wavelength increase ஆச்சுன்னா it is going to be, the order is ethylene diamine followed by ammonia and then finally water. Okay, so another one is which I did not discuss before is effective atomic number அப்படின்னு ஒரு term இருக்கு, effective atomic number. What is this effective atomic number அப்படின்னு பாத்தீங்கன்னா when the metals form complexes, when they form complexes, they try to what is the reason? Now another thing is why these metals form complexes அப்படின்னா actually they try to form, one of the explanation is they try to achieve the nearest noble gas configuration. Okay, general metal atoms also, by losing electrons also they can reach that, but gaining electrons also they can reach that. And for that in the effective atomic number அப்படின்னா number of electrons in the metal ion plus the number of electrons gained from the ligands, இது ரெண்டையும் add பண்ணீங்கன்னா, if you get closest noble gas configuration, okay, so they are stable. Okay, but of course there are other complexes are also there, but if they form nearest noble gas configuration, they are stable. If it is not, they are less stable அப்படின்னு அர்த்தம். Okay, that example they have given chromium hexaqua chromium 3 hexaqua chromium 3. Okay, chromiumத்துடைய atomic number என்னன்னு பார்த்தோம், 24. Okay, 24ல 3 electron போயிருச்சு, because chromium is in the 3 plus state, so 3 electrons are removed, so you have 24 minus 3, 21 இருக்கு. Okay, 21. And then aqua or aqua complex இருக்கு, ஆறுல ஒவ்வொரு ligandum 2 electrons கொடுக்கிறது, 6 times 2, then you get 12 electrons. So 21 plus 12 you get 33. Okay, of course here the effective atomic number rule is not obeyed, so you may be asked which among the following does not obey the effective atomic rule அப்படின்னு கேட்கலாம். So they may give which of the following obey the effective atomic rule அப்படின்னு கேட்கலாம், or based on the stability effective atomic rule tell which among the following is stable அப்படின்னு கேட்கலாம். So different ways they can ask. So if you look at this, if you look at the different complexes, they have given iron, potassium, இது வந்து hexacyanoferrate. Okay, hexacyanoferrate 2 பார்த்தீங்க அப்படின்னா iron in the +2 state, atomic number 26, atomic number 26, and then +2 oxidation state ல பார்த்தீங்க அப்படின்னா 2 electrons போயிருது, so 26 minus 2, 24. 24 plus 2 நமக்கு வந்து if it is a coordination 4 னா 12 8 add பண்ணோம், coordination number 6 னா you have to add 12 electrons. If it is 4 னா 4 times 2 8 electrons add பண்ணோம். All we have to do is, so atomic number 26 the +2 ங்கிறதுனால 24 plus 12 36. If it is 36, the closest noble gas is krypton. Krypton's atomic number is 36. Now look at copper 2 plus here. So copper 2 plus it forms +2 oxidation state 29 minus 2 not 27 plus 8, okay, 35. It can have only 35 electrons. And cobalt 3 plus 27 atomic number cobalt today minus 3 na 24 plus 12 36. Okay, it's a stable, the krypton it reached closest noble gas is configuration is krypton. And nickel CO4, nickel inge vandu oxidation state 0, atomic number 28 plus 8 36. And then tetracyanonickelate. Okay, tetracyanonickelate here +2 state, look at here, it is 28 minus 2, 26 plus 8, 34 தான் இருக்கு. Okay, it has effective atomic number is 34. If it reaches noble gas configuration, it is stable. Okay, so based on that we can you may be asked to arrange the complexes in increasing order of stability. Okay, and then chromium platinum, hexa chloro platinate 4 platinate 4 plus 4 state la irukku. So 78 atomic number 78. Now one more thing you must remember, students, I try to memorize that iron cobalt nickel. I told you iron cobalt nickel. Okay, iron cobalt nickel பாத்தீங்க அப்படின்னா iron 26, cobalt 27, nickel 28. Okay, so ironக்கு அப்படியே செகண்ட் கீழே இருக்கிறது பாத்தீங்க அப்படின்னா they are actually ruthenium, rhodium, palladium. Okay, ironக்கு கீழே என்ன இருக்கு? ருத்தீனியம். கோபால்ட்டுக்கு கீழே என்ன இருக்கு? ரோடியம். நிக்கலுக்கு கீழே பின்னாடி பெல்லாடியம். ஸோ நிக்கலுடைய கான்ஃபிகரேஷனா பெல்லாடியம். நிக்கலுக்கு என்னது? நம்ம 28ன்னு சொன்னேன், D8 கான்ஃபிகரேஷன். ஐ மீன் 2 + 8. அதே தான் இதுலயும் இருக்கும். 2 + 8 எலக்ட்ரான்ஸ் தான் இதுல இருக்கணும் பெல்லாடியத்துக்கு. அயனுக்கு 26, 2 + 6 அதே கான்ஃபிகரேஷன் தான் இங்க கீழே என்ன இருக்கு? ருத்தீனியம் இருக்கு. ஓகே, அண்ட் தென் கோபால்ட் எடுத்தீங்கன்னா 27 அதே தான் கீழே ரோடியம் இருக்கு. ஸோ இஃப் யூ மெமரைஸ் கோபால்ட்டுக்கு ஐ மீன் அயன் கோபால்ட் நிக்கலுக்கு கீழே என்ன இருக்கு? ருத்தீனியம், ரோடியம், பல்லாடியம், அந்த ஆர்டர் மறக்காம. ஓகே, அட்டாமிக் நம்பரும் ஈஸியா பண்ணிக்கலாம். எப்படி அப்படின்னா இன்கேஸ் மறந்துருச்சுன்னா அயன்ல இருந்து நெக்ஸ்ட் நீங்க என்ன ஆட் பண்ணணும்? 26 + 18 ஆட் பண்ணணும். நெக்ஸ்ட் வந்து 32 ஆட் பண்ணணும். ஸோ 26 + 18 44. ருத்தீனியத்தோடது 44. 44 + 32 76. நெக்ஸ்ட் ஆஸ்மியம். Okay, so third D series la pathina osmium, iridium, platinum. Okay, so if you remember this iron cobalt nickel keela enna irukku? Ruthenium, rhodium, palladium. Adukku keela enna irukku? Osmium, iridium, platinum. Adu naabagam vechukonga. Vechikna easy ah, you can, even if in case if you get confused you can get the atomic number, but mostly they will give atomic number for these elements. So adhe pola copper, silver, gold. Copper ku காப்பருடைய கான்ஃபிகரேஷனா தான் சில்வருக்கும் கோல்டுக்கும், பிகாஸ் தே ஆர் த சேம் குரூப். ஓகே, காப்பர் D29, so it is 29 is 4s1, s1 D10 கான்ஃபிகரேஷன். சில்வருக்கும் அதே தான் s1 D10, கோல்டுக்கும் அதே தான் s1 D10. ஜிங்க், கேட்மியம், மெர்க்குரிக்கும் அதே லாஸ்ட், அதே have s2 D10 configuration. They are on the same group. So based on that you can have this. Okay, okay, now let us look at some of the other problems. Okay, look at question number 16. Question number 16, IUPAC name of the coordination compound K3FeCN6 is அப்படின்னு கொடுத்திருக்காங்க. K3FeCN6 K3 இருக்கு, பிளஸ் K3 இருந்ததுன்னா கவுண்டர் அயான் 3+ இருக்கு, 3. ஸோ இங்க வந்து 3- இருக்கணும். ஸோ 6 சயனைடுக்கு வந்து -6- இருக்கு, இங்க வெளியில 3- இருக்கு. ஸோ இந்த பக்கம் கொண்டு வந்தீங்கன்னா பிளஸ். ஸோ அயன் இஸ் இன் 3 oxidation state. Okay, +3 state. So the name should be hexacyano. Cation anion இருக்கிறதுனால ஃபெரேட்னு வரணும். hexacyanoferrate 3, potassium hexacyanoferrate 3. ஸோ எங்க இருக்குன்னு பாருங்க. பொட்டாசியம் hexacyanoferrate 2 இருக்கு, ராங். பொட்டாசியம் hexacyanoferrate 3. ஓகே, பொட்டாசியம் hexacyano iron போட்டிருக்காங்க, ராங். அயன் வந்து வரக்கூடாது. ஏன் அப்படின்னா இட் இஸ் an anion, ஸோ ஃபெரேட் தான் வரணும். ஸோ ஆப்ஷன் 2 is the correct answer. Okay, and then look at question number 17. Which of the following compounds shows optical isomerism? Okay, optical isomerism general ஞாபகம் வச்சுக்கோங்க. There should be optical isomerism காமிக்கணும் அப்படின்னா there will be unsymmetry should be there. ரொம்ப காம்ப்ளிகேட்டடா இருக்கணும் அந்த மாலிக்யூல். இங்க பாத்தீங்கன்னா காப்பர் NH3 all are homoleptic ligands இருக்கு. optical isomerism not possible. ZnCl4 homoleptic all are same, not possible. Okay, cyanote all are cyanide, they all same, you cannot form. But only thing is here optical isomerism generally formed by didentate and polydentate ligands. Okay, it's oxalato, it's a polydentate ligand, so the option is 3. So trioxalato chromium complex will show optical isomerism. And then question number 18th pathina, which one of the following cyano complexes would exhibit the lowest value of paramagnetic behavior? Okay, lowest paramagnetic behavior அப்படின்னு கொடுத்திருக்காங்க. cyano, now we know that cyano ligand வந்து strong ligand. இந்த எல்லா காம்ப்ளெக்ஸ்லயும் cyano ligand தான் இருக்கு. So all of them going to form the low spin complex. அந்த லோலயே எது லோ அப்படின்னு கேக்குறாங்க. So based on that we have to find out the D என்ன கான்ஃபிகரேஷன் பார்க்கணும். ஃபர்ஸ்ட் வந்து குரோமியம் CN6 3- இருக்கு. So it is 3+ இருக்கு. So குரோமியம் 3+. குரோமியம் 3+. குரோமியத்துடைய அட்டாமிக் நம்பர் என்ன 24. 24 minus 24 என்னது? I mean 2 + 4 6 electrons இருக்கு. லாஸ்ட்ல 6 - 3 3. So number of and 3 D3 நம்ம ஏற்கனவே பார்த்தோம். D3ல வந்து whether it is low spin high spin எதா இருந்தாலும் 3 unpaired electron இருக்கும். So number of unpaired electron is 3 in chromium. And then look at here second one, and second one Mn CN6 3-. Again Mn is 3+. Of course all of them are in 3+ configuration. Mn 3+. So Mn 3+ உடைய configuration என்னன்னு பார்த்தோம். Mn வந்து 25, atomic number 25. அப்படின்னா 25 2 + 5 7 electrons are there. 7ல வந்து 3 போயிடுச்சு அப்படின்னா 4 electrons இருக்கும். ஸ்ட்ராங் ligands இருந்தது 4 electrons இருக்கு. அந்த 4 electrons வந்து எப்படி டிஸ்ட்ரிபியூட் ஆயிருக்கு? 4 electrons it will be first d orbital 2 இருக்கும், செகண்ட்ல 1 இருக்கும், தேர்ட்ல 1 இருக்கும். So 2 unpaired electron இருக்கு. Chromium 3 unpaired, magnesium 2 unpaired electrons. So let's come here. Fe3+. Fe3+ல பாத்தீங்க அப்படின்னா it is Fe. What is the atomic number of Fe? 26. 26னா 2 + 6 8 electrons இருக்கு வேலன்ஸ் ஷெல்ல. 8ல வந்து 3 ரிமூவ் பண்ணணும் அப்படின்னா 5. ஓகே, 5 இருக்கு. அந்த 5ஐயும் ஒவ்வொன்றும் ஃபர்ஸ்ட் போட்டுடுறோம் d ஆர்பிட்டல்ல. பட் தி திங் இஸ் சைனை வந்து ஸ்ட்ராங் லிகாண்ட் பேர் பண்ணிடணும். ஓகே, ஸோ 5 இருக்கிறதுல வந்து 2 இது பேர் ஆயிருது, மிச்சம் 1 தான் இருக்கு. ஸோ யூ ஹவ் 1 unpaired electron. ஸோ குரோமியம் இந்த காம்ப்ளெக்ஸ்ல ஃபர்ஸ்ட்ல வந்து 3 unpaired electron, செகண்ட்ல வந்து 2 unpaired electron, 3ல வந்து 1 unpaired electron இருக்கு. Now look at option 4, hexacyanoferrite cobalt 3+. கோபால்ட் உடைய ஆக்சிடேஷன் ஸ்டேட் என்ன? I mean atomic number என்ன? 27. 27னா 2 + 7 9 electrons இருக்கு. 9ல 3 போச்சுன்னா மிச்சம் 6. அந்த 6 since it is a hexacyanate is a strong ligand, 6 d orbital இருந்து d electron இருந்ததுன்னா அந்த 6மே இப்படி பேர் ஆயிரும். ஓகே, ஸோ இதுல வந்து no unpaired electrons. இங்க 4th வந்து unpaired electronே கிடையாது. ஸோ paramagnetic lowest value paramagneticனா iron, hexacyanoferrite ion தான். ஓகே, now look at second 16th question. 16 correct option is 2, and then 17 3, and then 18 lowest paramagnetic value கொடுத்திருக்காங்க 4. So there is which one exhibit the lowest value of paramagnetic behavior? Okay, I'll just find out that one. Okay, lowest paramagnetic value அப்படின்னா I'll let you know. Hello? Class முடிஞ்சதுங்க மேடம். Shall I come out? Okay.